Okay, hi everyone. I'm Trond Andersen from Google Quantum AI, and today I'm going to tell you about our recent development of a high-fidelity hybrid analog-digital quantum simulator. And I'm going to show you how we use that simulator to make some very interesting discoveries about the thermalization dynamics in an XY model in our system. To start out, let me first motivate this work a bit by talking about where we are today in the world of NISQ simulation. I think we've now really entered a very exciting era where we can really start using our quantum hardware to do very exciting things. We can use our quantum hardware to make discoveries, for instance, of bound states of microwave photons that had this very surprising resilience to integrability breaking that we really did not expect at the time of the experiment. So I would say this is very much a discovery made on the quantum hardware. We can also use our quantum hardware to realize completely new physical phenomena, for instance, the braiding of non-abelian anyons. And we can use our quantum hardware to answer interesting questions. For a while, there was a debate about the universality class of the Heisenberg dynamics in a spin chain. And by using quantum hardware, we were able to provide evidence that resolved that debate. So clearly, there's a lot of very exciting progress here. But at the same time, there are crucial challenges. One crucial challenge is, of course, decoherence, which limits how far into the dynamics we can simulate. In addition to that, in the digital world, which all of these three works are from, another important challenge is Trotter errors, which limits our ability to produce low temperature states. So that brings me to the advantages of analog quantum simulation. A key one is that in analog, we have very fast entanglement growth. That's what's shown on the left here, where we've simulated the entanglement entropy as a function of time, both for an analog circuit and also for an analogous digital circuit. And you can see that it grows much, much faster in the analog case, simply because all of the couplings are turned on at the same time instead of applying layers of digitized gates. In addition to that, by directly implementing the Hamiltonian dynamics, we avoid trotterization. That allows us to circumvent this sort of eternal issue of digital simulation, where a too small trotter step gives you decoherence because it's very slow, and a too large one gives you trotter error, as is shown here for the transverse field Ising model. But of course, analog simulation is not new. It has a very rich history. So a key question here is whether we can provide some new capabilities with our transmon platform. And I would say the answer to that is a very strong yes. We indeed have some key advantages that we can leverage. One of them is that we have a very fast repetition rate that allows us to do things such as measuring the full counting statistics, which is what we did for this Heisenberg universality class that I mentioned. We also have readout in all bases. If you combine that with this fast repetition rate, that gives you capabilities such as measuring the many-body entanglement in larger subsystems using randomized measurements. And actually, I want to take the second point here even further, because really what we have in our system is a very simple access to hybrid analog-digital operation. And this is kind of awesome because it really gives you the best of both worlds. It gives you the very fast entanglement growth of analog evolution, but then you can also use digital universal gates both to very flexibly prepare your initial state and also to very extensively characterize your final state. And you're going to see a lot of this in my talk today. However, unfortunately, there's no such thing as a free lunch. And in our case, really the big obstacle is that analog calibration is tricky. The reason for that is very intuitive. We want to perform some kind of local calibration, as is shown here. Typically, we want to calibrate 2 and 2 qubits. Now, in the digital case, after you're done calibrating those pairs, let's see. Maybe just bump in the HDMI. Fantastic. In the digital case, after you're done with that pairwise calibration, you're pretty much there, because really what you've calibrated is your entangling gates. You can put that together into a circuit. However, that's not the case in analog, because what we measure on the left here are hybridized quantities. They depend on the neighboring qubits and couplers. And so when we turn on all of the couplers at the same time in our full-scale experiment, these dressed hybridized quantities, they change. So therefore, we need a smarter way of moving from the left side here, our local calibration, to our full-scale global experiment. We tackled that challenge by developing a completely new, scalable see if we can just... Yeah, so to tackle this challenge, we developed a completely new, scalable, high-fidelity calibration scheme, where really the key idea is to explicitly calibrate the bare frequencies of the system. The reasoning behind that is that these bare frequencies do not change when you move from a local calibration setting to a global experiment. To extract these bare frequencies, we developed a set of carefully chosen 2-qubit spectroscopy measurements, shown on the left here. These allows us to extract all the information that we need about our system. We then feed that into a very advanced device model, including many levels in both the qubits and the couplers, and also all these various coupling pathways to really do things as accurately as possible. And by doing that, we're able to find the device Hamiltonian very, very accurately. And finally, we use a projection technique to simplify that to a spin Hamiltonian, which you see here. It's an XY model with some higher order terms that are typically about an order of magnitude smaller than the main terms. Okay, so now we've developed this new calibration scheme. First thing we have to do is to benchmark it to see what kind of fidelity we can achieve here. To do that, we perform an analog version of random circuit sampling. We apply first single qubit gates to half the qubits. We then turn on the analog evolution for some variable amount of time. And then finally, we measure the distribution of bit strings at the end of the circuit. Before comparing that with the theoretical distribution to estimate the XCB fidelity, let me just make a quick comment about the distribution that we actually observe. You can see here that we have an exponentially decaying distribution. It's a Porter-Thomas distribution, indicative of quantum chaos. But what I really want to draw your attention to is this inset here, where I plot how quickly it gets to that distribution. So a value of 1 here indicates that we're at the Porter-Thomas distribution. And you can see that after just a few cycles, 4 or 5 cycles, we're already in that distribution. So that's much, much faster than what we achieve in a digital case. That means that you can get to this very highly entangled point with much, much less effects of decoherence. So that's really the great advantage here. Now let's compare it to the theoretically predicted distribution that allows us to extract the fidelity. I plot that here as a function of time for various different system sizes. And you can see that even at 35 qubits, I can go up to 35 cycles. That's much, much longer than we needed to get to maximal entanglement. And I still have 30% of fidelity in my system. That's the full state fidelity. Said differently, the error of this calibration scheme is only 0.1% per qubit per cycle. That's a really, really low error, and that's not even taking into account the fact that the entanglement entropy was growing very fast during each one of those cycles, which makes it even better. I want to emphasize that this was really achieved through mainly just very careful physics modeling. The reason why that's important is that physics modeling is very scalable. So compared to some kind of blind optimization scheme where the number of parameters scales poorly with system size, here we really have a very, very scalable scheme. So this combination that we have here of fast entanglement growth, very high fidelity, makes this very computationally complex. And if you want to estimate this with the same fidelity, we find that this takes an estimated more than 1 million years on frontier at the full system size of 69 qubits. Another way to think about this combination of this very high fidelity and the fast entanglement growth is to consider what's called the mixed state entanglement proxy. That's a very intuitive measure. It's just a pure state entanglement entropy, but then corrected for the effects of infidelity, including both incoherent and coherent errors. And that's what I show on the right here for various different recent platforms. And you can see that our new platform in the top right here is very, very much competitive with other platforms. In particular, I want to draw your attention to how close it is to this diagonal dashed line, which represents the case of perfect fidelity. So first, this makes us very excited for the kind of physics that we can study with this new platform. And for the remainder of the talk, I'm going to tell you about our first physics study with this new platform. In this study, we're going to explore the rich phase diagram of the XY model. The way we're going to do that is we will first start with a very simple staggered Z-field Hamiltonian, just alternating fields up and down. We'll prepare the ground state of that Hamiltonian, which is just a simple antiferromagnet. And then we will ramp from that simple Hamiltonian to an XY model. Now, by varying the rate at which we perform that ramp, we're going to explore different paths through the phase diagram. And there are 2 particular features that I would like to draw your attention to and that we would like to look for. One of them is a Kosterlitz-Thouless transition. So we expect that if we manage to get to a sufficiently low temperature, we should see that free vortices become entropically unfavorable, and we should hopefully then see a change from exponentially decaying correlations to an algebraic decay. In addition to that, as we move through this phase diagram, there should be a point where the gap becomes smaller than the inverse of the remaining time. And then at that point, we expect that the system should sort of not be able to keep up anymore, should kind of freeze, and it should be stuck with a correlation length that is a power law in the ramp time. That's what's known as the Kibble-Zurek mechanism. There's been some beautiful studies of it in cold atoms in an Ising model, and here we wanted to study it in our XY model. So let's start out simple. Let's first look at the final state energy as a function of the ramp time. That's what's shown here, both for experiment in red and also simulation in blue. You can see that as we increase the ramp time, we manage to get to lower and lower temperatures. And actually, we get very close to the ground state, shown here in the dashed gray. We get 95% of the way there. And even better, we actually manage to get past the expected transition temperature for the Kosterlitz-Thouless transition. I want to quickly point out here that there are two experimental curves. One of them is labeled SQ, that's the sort of standard single qubit measurements where I measure XX correlations, that's my energy, by measuring X on one qubit, X on the other, and I find the correlations. But then I can also perform a conversion to the Bell basis. I can do that because I have 2 qubit gates as part of my analog evolution. I can switch back and forth between analog and digital, no problem. That allows me then in the Bell basis to measure not just the energy, but also the total number of photons, so total Z. These are commuting variables, so it's no problem to measure both. And that allows me to post-select on photon number conservation, and it gives me a better answer. So that already shows one of the advantages of having entangled gates as part of our analog evolution. Okay, so these were XXYY correlators. That's the energy, just nearest neighbor. Let's now look for some more interesting physics by going to longer range correlations. Here I introduce this G of R, which is just the average correlations between pairs of qubits separated by R. I plot it here for different ramp times, and you can see that at the longest ramp times, we really get correlations that extend across the entire device. This is much better than we would be able to produce with a digital protocol. To learn more about this, we can now perform a radial average. That gives me here the magnitude of correlations as a function of the distance. And here we already start seeing something quite interesting. You can see that at very short ramp times, I have something that looks mainly exponentially decaying. But then at longer ramp times, I find something that has this clear kink in it. It looks more like a power law decay. So to study that further, let's take a look at a few different signatures of the KT transition. I'll start out very simple, just with the energy. I already showed you that the energy goes below the expected transition point. But then let's also look at the form of the decay of the correlations. And to do that, I'm going to plot a ratio here. It's the ratio of the error that I make in a power law fit and the error that I make from an exponential fit. What I find then is that at some point, this ratio suddenly has this very steep drop. It's exactly the same regime as when I go into the low temperature regime above. And this is indicative of our correlations decaying more and more with a power law character and less with an exponential character. Another very neat signature that we can look at is the power law exponent. This exponent is expected to take a universal value of 1/4. I plot the exponent here, and indeed, I find that it goes very close to 1/4. It's about 0.28. Finally, we can take an even more direct look at this and really just go and measure the vortex density. That's what the Kosterlitz-Thouless transition is all about. I can measure the vortex density by measuring the spin current around each plaquette. I square that operator because I don't expect any net vorticity in my system, so I'm looking at the fluctuations. And when I do that, I find this very sharp drop in the vortex density. Now I want to emphasize that this operator that we're measuring here involves several different, it's a sum of Pauli strings of 4 qubits and 2 qubits and so on. That's no problem. In our platform, we can measure any kind of correlator like this. Okay, so that was the KT transition, but I mentioned that we also wanted to look at some Kibble-Zurek physics. So here on the left, I show you the correlation length as a function of ramp time. And I've included here the prediction of the Kibble-Zurek mechanism. You can immediately see that our experiment and the simulations do not agree with that prediction at all. That was initially very worrying to us. We were trying to figure out what was going wrong here. And as part of that, we decided to not just measure the correlations at the end of the ramp, but also throughout the ramp. That's what I show you on the right here for a few different ramp times. I've also included these diamonds here to show you the point where we expect from Kibble-Zurek that the system should freeze and get stuck with a certain correlation length. What you can immediately see is that's not true. These correlations definitely don't get stuck. They keep growing actually by a lot beyond that point. What you're seeing here is the coarsening of the correlated domains, which causes a breakdown of the celebrated Kibble-Zurek mechanism. What we can do now is we can also take these points and bring them back to the left plot. That's sort of like pretending that this additional coarsening did not happen. If we do that, we now find a very good agreement. So that's a nice sanity check. Yeah? There's some effects of finite size. That's not at all enough to cause the breakdown of Kibble-Zurek. It is true that I'm in no way claiming that this is exactly the same as the thermodynamic limit. But no, that's not what's driving it here. Even the finite size is not giving this coarsening behavior. And I'll show you more of an actual picture of the coarsening in a minute. What we can do then to learn even more about this is we can now go and rescale the axes. So I'm here going to rescale the x-axis by the freezing time. By that I mean how long before the critical point should the system freeze. And I can rescale the y-axis by the correlation length at that freezing point. When I do that, I find that these curves that were initially completely branched out actually collapse very nicely on top of each other. This is in perfect agreement with the recent theoretical predictions of a universal coarsening behavior causing these kind of breakdowns of the Kibble-Zurek mechanism. And I want to emphasize that this collapse really extends far beyond just the quantum critical regime. It's also seen far beyond this. And that's suggesting that this is more of a dynamical universality driven by coarsening and not just a kind of extended Kibble-Zurek mechanism. Okay, so far we've been tuning our system by varying the ramp rate. I'm now going to make a slight change of gears. And now we're going to try to tune it instead by injecting energy at the very beginning of our experiment. You might remember that we started out with this antiferromagnetic state. That was the ground state of this simple staggered field Hamiltonian. What I can do then to inject energy is I can flip some of those spins at the very beginning. That's what I've done on the left. So here on the x-axis, I sweep how many excitations I've injected. And I then find that the final energy is also perfectly tunable. As I add more and more initial excitations, I can very nicely tune the energy of my final system. And I've also done that here for multiple ramp times. Simultaneously, when I add more and more excitations, I also see the correlation length drops, just as expected. But really, to get the full insights of this data set, what we should do is we should take all of these points and plot them on the same axes with the correlation length on one axis and a function of the energy on the other axis. When we do that, we find that all these data points corresponding to many different ways of preparing the state, either some initial excitations, a certain ramp time, all these combinations, the points all collapse. And this makes perfect sense because we know from the eigenstate thermalization hypothesis that if I give you two states, one that I prepared with some combination of ramp time and excitations, another that I prepared with some other combination, if they have the same energy and the system is thermalized, I should see the same observables. And that's exactly what I see both for the correlation length here and also for the vortex density in the inset. So far, we've tuned our system both with a ramp rate and with initial excitations. 10 minutes. I have 10 minutes more. Oh, really? Wow, that's very kind. Okay, yeah, good. So we've tuned it in two different ways. These are very nice. They give us a lot of tunability. But they have one central limitation, which is that in order to get a substantial amount of correlations, I need to ramp very, very slowly. And by the time I get to that final state, a lot of the thermalization dynamics are already over. As a consequence, in a lot of what I've shown you today, I've shown you end results of thermalization, but I never really showed you a lot of the thermalization dynamics themselves. In addition to that, with these tuning techniques, we're only able to tune the energy. There are, of course, other observables that we would like to be able to tune in our system as well. That motivates the last part of the presentation, where we are now going to take full advantage of our hybrid analog-digital in order to digitally prepare pairwise entangled initial states. What's really nice about that is that that allows us to inject correlations, or energy if you want, from the very beginning, so that I don't need to ramp for a very long time. I can just go and turn on my analog evolution, and I can now really watch the thermalization dynamics real time finally. In addition to that, as you'll see, this will also allow us to tune not just the energy, but also other observables, such as vorticity, and it's going to allow us to tune the spatial distribution of it. Specifically, we're going to prepare this kind of dimer state that you see here, characterized by this phase phi. That allows us to tune, for instance, the energy. If I use a phi of 0, I get some very positive energy. If I use a phi of pi, I can inject some negative energy. But I can also use a phi of pi over 2 that allows me now to inject spin currents. There are really endless possibilities with this kind of capabilities. So let's put it to the test. We'll start with the simplest case. Here I'm just going to inject negative energy in 1 out of 4 bonds. That's what I've done in the initial state here. And now I can really watch how that energy spreads out in the system. And I want to draw your attention to the time scales here. After less than 1.5 cycles, you can see it's almost already perfectly spread out. Simultaneously, we can look at the correlations during this thermalization process. You can see the correlations go from being this very short-ranged to over just 1.5 cycles, being now a much longer correlation length corresponding to the value expected from ETH instead. So now finally we're watching the coarsening dynamics that I told you caused this, this Kibble-Zurek breakdown. Now we're watching it really real time. But we don't have to stop there. We can go even further. We can now also inject some positive energy on one side, negative on the other. That allows me to study completely different types of dynamics. Here I'm really studying the transport of energy from one side to the other. And notice that the time scale now is entirely different. It used to be 1.5 cycles. This is more than 10 times longer, and you still see an imbalance in energy. So by using this digital analog capability, I can tune myself into completely different types of dynamics in my system. On the right here, I've plotted some vertical cuts. So each color corresponds to one vertical cut, and then I plotted as a function of time the mean energy along that cut. I do that just to make a comparison with a simple diffusion model characterized just by a single diffusion parameter. And you can see that we have excellent agreement. It's almost a bit hard to see the theoretical curve, but it's yeah, the dashed one that's really right behind the data points all along. To take this even one step further, we can now move away from just tuning energy. We can start also playing with spin currents. As I mentioned previously, all we have to do is use a phase of pi over 2 instead of 0 and pi. That allows me to set up this pattern of spin currents. And now I'm really looking at the thermalization of that spin current as a function of time. You can see that we're now back to super fast dynamics again. This is less than a cycle, and it's almost completely gone. So we went from some very fast energy thermalization to some very slow energy transport, and now to some very fast current thermalization. And this is all made possible by the fact that we have this analog digital platform. I've also plotted here the vorticity. That's just a spin current around each plaquette. And of course, again, we see this very fast relaxation of about 1.2 cycles. That brings me to the summary of the presentation. I showed you that we developed this completely new scalable calibration scheme for high-fidelity analog evolution that allowed us to get an error of only 0.1% per cycle. And that made this very, very difficult to simulate classically with the same fidelity. And we were able to show that this will take more than 1 million years if you want to do it for the full system size. We then also added digital gates to this high-fidelity analog evolution. That gives us then both this very flexible initial state preparation and also a very extensive set of final state characterization techniques. And using these, we were able to see some very interesting physics. We saw both the signatures of the KT transition. We saw some nice effects of the eigenstate thermalization hypothesis. And then we also observed this very interesting breakdown of the Kibble-Zurek mechanism due to coarsening. So finally, I'd like to say that we're very excited about this new platform that we have here, and we really hope to use this for a wide range of beyond classical studies of quantum many-body phenomena. So with that, I'll just leave pictures here of everyone who's helped out with this, and of course, a thank you to the entire Google Quantum AI team, and thanks to all of you. I'll be happy to take questions.
Yeah, I have a quick question. You have shown the fidelity through XEB measurement, which is very impressive, 0.1 per cycle. But this is averaged out, which is essentially a depolarizing channel, right? And what is the error budget in regard to different source of error? And what is the susceptibility of this simulation to different type of error?
That's a great question. So we can actually probe the effects of incoherent versus coherent errors by looking at the self-XEB. The self-XEB was the quantity that we used in order to look at how close we're to the Poirier-Thomas distribution. It's just the XEB with itself. From that, we actually find that the effects of incoherent errors are almost surprisingly small. And I think there's actually quite a lot of interesting physics there, where there's several of these incoherent errors that you end up being less sensitive to in analog than in digital. There's some nice papers explaining why one should actually, for instance, dephasing ends up having a weaker effect because you sort of get an averaging. Your states are very delocalized and they feel sort of an average of the qubit frequencies instead of just feeling the energy very locally. So we were kind of positively surprised to see that the effect of incoherent errors are actually not the limiting factor, and it's still really the control error. Even though we spent a very long time, you saw the advanced device model, we spent a lot of time really trying to nail down every source of coupling and so on, but that still seems to be the piece that's limiting us. So I think one could possibly still improve it even further by making the model even better. Yeah.
Thanks. Any other questions?
Yeah, really wonderful presentation. I wanted to build on Murphy's question. So what were the order of the timescales with respect to the experiments? Like, did we need to worry about long-term drift or other sort of time-varying errors in miscalibrations?
Yes, that's a great question. I would say after 2 days, I would typically recalibrate if I want really high fidelity data. It's always a bit tough with these drifts. I mean, sometimes you get kind of a surprising drift where you can, I mean, someone opened the door or something, right? It's not like this drift is perfectly linear and I can give you an immediate time scale. But yeah, I would say that's the main limiting factor to XCB, and typically I would recalibrate a couple of times a week, kind of.
Well, I guess I'm also asking, like, to what degree was there like intershot variability? So you're saying that
I would say sorry to interrupt, but I hope this answers your question. I would say the limiting factor to fidelity is just that your Hamiltonian is not perfectly correct, and you will mainly see changes in that just because there's some slight change to the z function of a particular bias line or something like that. Yeah.
Any other question?
Yep.
Why do you start with a staggered state in the initial experiment with the chain?
So I want to start in some ground state. Of course, you could start with some other Hamiltonian that would allow you to be in the ground state. I'm actually not sure how well you would do if, it's a good question, could you start with just all ones on sort of the right half? I haven't tried that. I agree that should also be the ground state of the initial Hamiltonian and should in principle work. I guess one could kind of imagine that this is not completely optimal because you would have to shift a lot of photon population from one side to the other. It's kind of nice that it's already sort of spread out. But yeah.
I mean, as long as you are in a phase other than the final phase,
Yeah.
you should still get a similar behavior if you start with different Hamiltonians.
So I should say we haven't tried a lot of other Hamiltonians than this, but certainly, I mean, just starting with, of course, a uniform Z field, for instance, would certainly not work. Yeah, I guess that's, I could also say we've done some variations of the amplitude of this staggered Z field, and you can kind of clearly see that if it's somewhat small compared to G, it doesn't work very well, so you really need this staggered amplitude to be kind of substantial compared to G. Yeah.
Great. One more question.
Oh, you can use it. We use it tons for measurements actually. So all of these polystrings that we measure for the vortex density operator. We also do a measurement, I didn't show you, but we also do a measurement of the energy fluctuations, total energy fluctuations. So that's a bunch of different types of polystrings. That's all, of course, because we can measure whichever polystring you want. That's no problem. And also we can do these Bell basis measurements that I mentioned, where we are applying a 2-qubit gate right before the measurement. So there we're also sort of taking advantage of having 2-qubit gates that you can apply really whenever you want. And it doesn't have to be before and after. You could do it in the middle as well. We do, well, it's not published yet, but we definitely do experiments where you kind of stop the analog evolution. You do something in the middle and so on as well. So yeah, endless opportunities. I think this is just the beginning of starting to combine these things together.
Very exciting, endless opportunity. We will conclude with that. And so our next, we'll go into coffee break and we will start again at 10:50 in 20 minutes.